for the last module of chapter 10, let's talk about bond energies and bond orders. We're going to talk about bond order, bond length, bond strength. We talked about this a little bit already, about how we know a triple bond is shorter and stronger than a double bond is shorter and stronger than a single bond. But we really want to go into using bond energies to be able to estimate the amount of energy either consumed or released when a bond is actually formed. First, what is bond energy? Bond energy is defined as the energy required to break apart 1 mole of the bonds in a gas phase. So again, why are we measuring things in the gas phase? Because in the gas phase, we've basically overcome all of your intermolecular forces. We're going to talk about that in the next chapter, but all the attractive forces holding these molecules together. So instead of having to overcome the intermolecular forces, the attractive forces of the molecules within one another, we're just looking within one molecule now. So how much energy is it required to break apart 1 mole of all of the bonds that we're looking at, but in the gas phase? It is always positive. It's a positive value because it takes energy to break a bond. Remember, breaking a bond, endothermic. So of the bonds listed below, which is expected to have the highest bond energy? We've got a CC single bond, a CC double bond, a CO single bond, and a CO double bond. First, we need to remember triple bonds, shorter and stronger than double bonds. And double bonds shorter and stronger than single bonds. I apologize if this is really messy. I'm trying to do this very last minute for you guys because I never realized I didn't record these videos a year ago. And so I'm not sitting nicely at a table to do this right now. So if I want to know what's going to have the highest bond energy, well, the higher bond energy is going to be the stronger bond, right? Higher bond energy, stronger bond. So which one's stronger? Well, not my singles. Why? Because doubles are shorter and stronger than single bonds. So now I'm between carbon-carbon double bond and carbon-oxygen double bond. Which one's going to be higher? How do I determine that? The truth is, my higher one is going to be my carbon-oxygen double bond. What's the difference between these two molecules? This is polar, and this is nonpolar. That polarity is an unequal sharing of that electron density, right? Oxygen is more electronegative than carbon. Therefore, it's going to pull the electron density to itself. So oxygen is kind of like, yeah, I'll share with you a little bit, but really I'm going to pull your electron density to myself. It just makes it stronger. It makes it stronger because it's harder to break that polarity apart. If I was going to rank these in order from least to greatest, my carbon-carbon would be the weakest, followed by carbon-oxygen. When I say that, I mean my single bonds, followed by my carbon-carbon double bond, and my carbon-oxygen double bond. So bond energies. We can use bond energies to estimate the delta H for an overall reaction. So it's kind of going back to chapter 7 when we learned about using like the Hess's law, products minus reactants using delta H formation. We're going to do the same thing here. We're going to use bond energy instead. Again, bond energy, the energy it requires to break apart 1 mole of the bonds that we're looking at in the gas phase. There are 3 keys to doing this kind of problem. First thing you should do is rewrite the balanced equation with Lewis structures of each reactant and product shown. Second thing you want to do is identify which bonds are broken and which bonds are formed. Why? Because bonds that are broken take energy. It's endothermic to break a bond. Bonds that are formed release energy. Because bond formation is exothermic. Remember, bond breaking is always positive value because it's an endothermic process. The energy is going in. Bond formation is always negative because it's an exothermic process. The energy's been released when those bonds are formed. And then we use your just Huss's law equation. So let's do some examples. First, here's what the bond energies look like. And you would be provided with these numbers if you had to do these examples. You cannot do it without the values. You wouldn't know these values. But note what it's showing here. It's showing you the actual bonds. So like for a hydrogen-hydrogen single bond, it's 436 kilojoules per mole. What that means is to break up one hydrogen-hydrogen double bond, 1 mole of those bonds will take 436 kilojoules. If I have a nitrogen-oxygen double bond, it's 590 for 1 mole, 590 kilojoules per 1 mole of nitrogen-oxygen double bonds. So you do have to pay attention because like carbon-oxygen single bond versus double bond versus triple bond have different values. This has a star here because it's really small. There it is. I have to move the screen slightly so I can see a little better. Carbon-oxygen double bond and a carbon-oxygen double bond in CO2. So just a general carbon-oxygen double bond has a bond energy of 736. But in CO2 specifically, remember CO2 looks like this, it's actually 799. So that would be 799 here and 799 here. It's a very strong little molecule. So again, I will provide these values, but let's go ahead and work these examples. Because of space, I'm going to quickly white out some of this so we have some space to work. Because again, these slides are definitely designed to work on a whiteboard, not so much to write on a screen. And I did not plan ahead this time. Because again, for whatever reason, these videos were never made. Don't know why. Probably got bored. Very possible. Nothing against you guys. They're just not the most fun thing to do. Okay. Hopefully that gives me enough space. So, use the bond dissociation energies listed on the table. Calculate the approximate delta H for the following reaction. CH4 plus 2Cl2, giving me CH2Cl2 and 2HCl. Easiest way to do it is to redraw your balanced equation, but with the Lewis structures of each reactant and product shown. So if I've got methane, methane looks like this. This is going to react with 2 moles of Cl2, producing 1 mole of dichloromethane. Helps when you put the dichloral part there. ClCl, and 2 moles of HCl. I'm then going to think about what bonds are broken and what bonds are formed. Some students like to just look specifically and see which bonds are broken or formed. I like to break everything and then form everything because then it's just easier. So what I mean by that is I've got 1, 2, 3, 4 carbon-hydrogen bonds that need to be broken here. And that is 414 kilojoules per mole. Here, I've got 2, because I've got the 2 in front, 2 ClCl bonds that need to be formed, and a ClCl bond is 243 kilojoules per mole. Over here, 2 carbon-chlorine bond formed, which 339. And 1, 2 carbon-hydrogen bonds, 414 kilojoules per mole. And again, 2 HCl, 2 times 431 kilojoules per mole. 2 because of 2 in front. Next thing you have to do, you're almost done, by the way. Next thing you have to do is remember that bond breaking is always positive. Bond formation is always negative. There you can see it. Negative number there, negative number here, and negative number here. Bond energies are always reported as positive numbers. If I'm breaking it, I'm doing the opposite of forming, therefore I change the number to a negative number. So in my calculator, I'm going to say 4 times 414 plus 2 times 243 minus 2 times 339 minus 2 times 414 minus 2 times 431. And I'm getting an answer here, negative 226 kilojoules per mole. So this here, negative 226 kilojoules per mole. Again, these are all in kilojoules per mole, or sorry, not kilojoules per mole, kilojoules. I'll explain just a sec why. These are all kilojoules per mole, but these are the number of moles. So your moles have canceled out, giving you just kilojoules. Units is in kilojoules here. Add that up in your calculator. Again, negative on your products formed, positive on your reactants because they're broken apart. But I could write the complete thermochemical equation now. CH4 gas, 2 Cl2 gas, CH2 Cl2 gas, 2 HCl gas. And remember, for complete thermochemical equation, all you do is add your delta H reaction on there. And this is in negative 226 kilojoules. And I don't have to write per mole there because since it's written in the balanced equation, it's assuming per mole. It means negative 226 kilojoules of heat are released for every 1 mole of methane consumed, every 2 moles of Cl2 consumed, every 1 mole of CH2Cl2 produced, or every 2 moles of HCl produced. So if I wanted it for, say, 1 mole of HCl produced, I would divide that number by 2. It would be 113 kilojoules for every 1 mole of HCl produced, because this value here is correlating to the coefficients on the reaction itself. Let's look at the other two examples. Determine the heat of combustion of methane. So CH4 going to react with 2 moles of O2 gas, producing CO2 gas and 2 moles of water. Write that out by Lewis structure. I really need more room on this slide. When I look here, I've got 1, 2, 3, 4 CH bonds being broken. Here, 2 oxygen-oxygen double bonds being broken. Here, 2 CO double bonds being broken, but that is in CO2 specifically. You gotta pay attention to that. And here, 1, 2, but there's a 2 in front, 4 OH bonds being broken. So, because I definitely don't have room. Let's see, CH bonds. Got 414. I've got 4 of them, and it's going to be positive because it's a reactant side. My oxygen double bond in O2. I've got 2 of those, also positive because it's a reactant side. CO2. Or CO in CO2. I've got 2 of that bond, and it will be negative because it's being formed. And the reason the bonds are being formed is to lower the energy. And then the OH bond, I have 4 of those as well, forming 2 moles of H2O, but it's going to be negative. Again, negative here because it's being formed. Add all of that up, and I'm going to get a delta H reaction of 802 kilojoules per mole. Let's write that out. CH4 gas, 2 O2 gas, CO2 gas, 2 H2O liquid, delta H, the reaction here will be negative 802 kilojoules. And again, I'm not going to specify per mole there, because it's implied in the equation. So 802 kilojoules is released for every 1 mole of CH4 reacted or consumed. 802 kilojoules of heat is released for every 2 moles of O2. So it'd be 401 kilojoules for every 1 mole of O2, because I would divide by 2, right? 802 kilojoules of heat is released for every 1 mole of CO2 produced, and for every 2 moles of water produced. And the last one, the standard enthalpy of formation of H2O2 is negative 136. So you guys can actually read, I'm sorry. Negative 136 kilojoules per mole. Use this information along with the bond energies in the table, I should definitely say table, to estimate the bond energy of an oxygen-oxygen double bond. Or oxygen-oxygen single bond. I apologize. So, erase, or write everything down that you need to write down. I need to erase because I really need space here. So, I'm saying that I've got H2 plus O2 giving me H2O2. H2 looks like this, O2 looks like this, and H2O2, hydrogen peroxide, looks like this. I know that negative 136 kilojoules per mole of peroxide, so it's like this, delta H reaction is negative 136 kilojoules. That's what it's telling me. I know that it has to equal 1 HH bond breaking apart, that's definitely double bond. 1 oxygen-oxygen double bond. Those are both positives, they're both reactants. And here, so much stuff here. I have 2 oxygen-hydrogen bonds. So minus 2 oxygen-hydrogen is here. Minus 2 times 464 kilojoules per mole. Minus the value for that OO bond. Basically, this is what I'm solving for algebraically. And I find that OO bond has a bond energy of negative 142 kilojoules per mole. It's pretty low, right? Hydrogen peroxide is very reactive. That oxygen-oxygen single bond is actually a really weak bond and relatively simple to break apart comparative to other bonds. Like, look at CO2, the carbon-oxygen double bond in CO2. It's really, really high comparative to that. That oxygen-oxygen single bond is a weak bond. That's why hydrogen peroxide is so reactive.